lots of people say, well, I can tell your stuff is real because you've got snapshot failures in your test log. And you know, we triage and investigate all these failures. You know, I've got high confidence that the current failures are known issues in the verification environment and aren't RTL problems. So, we've got 3 fully verified IP. Go and use it to be confident to take out in a big commercial shipment content. Fantastic, right? Well, yes, but really there's more to it. It is a mistake to consider open source, open silicon, as just great free stuff. Go use it. I mean, please do. And, you know, you can do it like that. But to make the most of this, it really, you've got to understand it's a whole different way of engineering, a whole new set of working practices. And if you fully engage with those working practices, there's lots of benefits to be had. So for one thing, you know, you've got full access to the IBEX RTL, and you can do whatever you like with it. It's licensed under Apache 2, by the way, it's a very permissive license. And because you've got all of our DB, if you want to say, make some modifications to IBEX, you can run the whole verification suite and check that it still works. You may need to make some modifications, add some extra scenarios, hit the new functionality, what have you, but you know, that ends up being a minor tweak, and then you've got your customized IBEX, fully verification closed, ready to take out with, you know, not much work. And then the other thing is when you've got multiple parties working together to build something, you can often end up with a better design, with kind of less total use or simple compared to if you did it all kind of in-house with a siloed team. We don't have commercial pressure to gatekeep improvements behind yearly releases. You know, when we were developing the bit support, that was just steadily feeding into the repository bit by bit, and you could pick it up, and as soon as you wanted to, you just go and use it. And you didn't have to wait for, you know, next year's release and pay us another $100,000 to take it and use it. And you've got freedom to kind of configure things if you want. We don't have marketing and sales teams spinning the bingo machine and telling us that, well, we need the IBEX 8478S, slightly lower performing, but does have the security features, or the A48, the A480, higher performance, with different information. Great, well, none of that, it's just IBEX, so there's all kinds of different possibilities you can do with it. Final thing here is that contributing partners are vital, because as I say, really open source isn't free, and by contributing there, you know, I do mean money is really important, and also engineering resources, expertise, compute tools, etc. And this is what the Open Title Partnership provides for loans. So, final plea here is, one of the frustrating things about working in open source is you often don't know what people are doing with your technology, and that's kind of by design. But you know, I know there's awful lot of IBEX users out there, but unfortunately I can't splash on the big slide box logos and take our numbers, because I know some of that, but I basically don't know what I can talk about publicly, because most of it's been told to me informally or under specific NDAs. And I'm always talking to more and more people who are saying, oh, I'm using IBEX for that, oh, I've taken out IBEX. So it'd be fantastic to hear from more of you. So if you are using IBEX, or you're interested in supporting our work or helping drive development of IBEX, well, please do get in touch. There's that info at email address with Lotus. And my contact details are here. And final little hiring plug, we are now hiring, so if in particular, if you're interested in doing TV work or open source silicon and interested in exploring kind of new innovative ways to do it, then yeah, check out the website, check out the quiz. So, thank you very much for your time. I have been great chatting.
So we have a minute or two, so we can take a few questions. Any questions on this quite exciting technology, or actually this quite exciting open source to usable commercial technology experiment? Hey, come on, Alan. You promised me a question every talk.
Architectural compatibility tests. See, how can we get hold of your PMP tests?
They are in the repository. I can point you towards where they are. They're partially derived from some tests that whoever did the EPMP support in Spike wrote to validate their implementation. We've pulled in some of those, and we've kind of got our own extra bits in there as well. But it's all available in the IBEX repository.
More importantly, where can we get hold of the coverage models?
So that is, part of that comes from Risk DB, and part of that, the PMP coverage models are all within IBEX. They're not super specialized in the IBEX microarchitecture, but they're not like completely, you couldn't just immediately apply one to any core, but it could be used as a model for a more generic coverage model.
Well, we probably want to actually make it less specialized.
Yes, yeah.
Thanks.
Well, on that, I have just one remark. So open source lives from the contributions. So if you have POP tests and you're using them, it would be great if you engaged with the ACT group as well and contributed that. We have exactly the same problem you have. Yeah, that's about international. Any further questions? I know it's a long day, but all right, I guess. That is a great thanks for the talk, great thanks for the presentation, and thank you for your time. So our next speaker is Martin Wagner, who is a PhD student at TU Leuven and doing research together with INET HistoryNet. So his research work is in the area of how to design sanction-led attacks, formal verification, both on the offensive and defensive side of the research. Always love your security researchers. Nobody else can pull off saying offensive and defensive in a pile. Contributing to a number of projects on sanctions. So the title of the talk is Proteus, an extensible RISC-V for hardware extensions.
Hi everyone. It's nice to see that there are still so many people for the last session. So I will be talking about Proteus, which is this RISC-V core that we developed at our research group, HistoryNet. And the keyword is extensibility. So, for example, when you think about RISC-V, the instructions and architecture, you think it's an open standard, it's an easily extensible standard. So if you want to implement your own instructions, your own CSR registers, it's very easily doable, as also evidenced by all the official extensions and also custom extensions that people have developed for their own custom purposes. So we thought it's nice that we have this easily extensible instruction set, but it would be great to have a CPU which enables you to take these extensions to the ISA and implement them easily in hardware, so that afterwards you can run some benchmarks, run some tests, do some evaluation, whatever your heart desires. So for this reason, we created Proteus, one of the many 32-bit RISC-V cores. So what makes this special? And how do we focus on extensibility? One of the things is that it's written in spinal HDL, which is a DSL embedded in Scala. So even mere mortals like myself who don't know too much Verilog or VHDL can more easily get started with the development. I will have an example of spinal HDL code later on in the slides. Even more importantly, the design of the CPU is based on a plugin system, which we took inspiration from Beck's RISC-V, which was actually created by the same developer who created Spinal HDL. I will also explain this plugin system in more detail in the next slide. Proteus comes with two implementations. We have both an in-order simple 5-stage pipeline and also an out-of-order design with parallel execution units. And both of these pipelines implement the 32-bit integer and multiplication instruction sets and the CSR extension. Both of them pass the official RISC-V unit test, but we've also run more extensive cryptographic and benchmark focus already. And this is enabled by the board support package, the board support package that we wrote for you, so that you can just take C programs, compile them for Proteus, and run them on either pipeline. So let's dive into the details of this plugin architecture. I'm sure most of you are familiar with this pipeline schematic. So these are the stages that an instruction travels through during its execution. So we have instruction fetch, decode, execution, memory operations, and register write-back. You can also think of this pipeline as interactions between the pipeline registers. So between each stage, there is a pipeline register, and during the instructions execution, data travels through these pipeline registers, and in between the stage, you find some logic, some operations on this data that is propagated. And our plugins plug into between these pipeline registers. So basically, when you are writing a plugin, you can define, okay, I want to take some values from the previous pipeline register. I want to do some logical operations on it, some arithmetic, whatever you want. And then I want to write that into the output pipeline register. So here you can also see an example of some spinal HDL code. In the first line, you can see that we take some input from the input pipeline registers, for example, the ALU operation, and then on the last lines, after performing some operation on it, you can just write this into the output pipeline register. And this whole thing is written in this abstract manner, so you can take the plugins and just plug it into whichever stage you want. And you can even modify this later. It's also possible to write plugins that modify multiple stages or that propagate data across stages in the pipeline. For example, this blue one represents a branch predictor, where in the execute stage, we look at the instruction that's currently executing. We check, is this a branch? What was the branch target? Was the branch condition met or not? And based on that, we can update the table, which is then consulted from the fetch stage, where the instruction fetcher decides, based on this branch history table, which next instruction it should fetch. So far, I've talked about the in-order pipeline, but as I mentioned before, we also have an out-of-order implementation. This feature is the textbook algorithm of Thomas-Lu to perform register renaming and scheduling of the instructions.